Please join me in welcoming to the Distinctive Voices podium, Dr. Sharon Wood.
It's really a pleasure to be here tonight. I'm going to talk a little bit about urban infrastructure. I will not be talking about earthquake engineering. Since I moved to Texas, the earthquake risk is actually quite low there, and my interests changed to some other areas. So I'm sure many of you have seen that the National Academy of Engineering has grand challenges for the 21st century. And one of those is restoring and improving urban infrastructure. So that's the area that I've been working in recently. I think this photograph is a wonderful example of the urban infrastructure because it's all the systems that we need to live in the way that we're accustomed to living today. So we have the bridge, the buildings, we see the electrical infrastructure, there's a communications tower there, so we see communications. We've got the bay, so that's a port facility. We don't see the buried pipelines for water and wastewater, but you can envision them. So I think this really captures what we mean by urban infrastructure. Now, a lot of the background related to urban infrastructure and really trying to evaluate it was done by the American Society of Civil Engineers. They started in around, it was around 10 years ago, where they would give a report card every few years that gave grades to each of the different systems. And you can see here we've got some water treatment plants, some electrical grids, airports. They basically characterize the infrastructure in a variety of categories. And this is how they went through and evaluated each one and gave grades to them. Now, I think the thing that shocks everyone is to see that there's a grade of D+ is what they evaluate the grade of our infrastructure is. And secondly, that the estimate is $3.6 trillion needs to be invested by 2020 to bring our infrastructure up to the point where we have a very good rating, a rating of B. And that number is actually mind-boggling. Okay? So the work that I've been doing is related to bridges. So even though it has a fairly high grade here, that's what I'd like to talk about. I think there are a number of examples, or there are analogies that can be drawn to these other types of systems. But as I mentioned, I've been working on bridges. I also think that we notice bridges a lot more because we drive over them every day. We have examples of bridges that are just icons for us. I'll show you a few examples. You don't feel the same way about the water treatment plant that you might feel about a signature bridge. So the information that in the NAE, in their description of the Grand Challenge, they start off with a discussion that the infrastructure is aging and failing. And that's because the infrastructure has been built up over the course of over 100 years. And so we have some very old components. And they're usually the components that are in the center of the cities because that's where the infrastructure was needed first. So that is one of the challenges. The second challenge is that the amount that we're investing in repairing and maintaining our infrastructure, that percentage of the total amount of tax funding has been going down. And I think that's because our population is growing. We have a lot of needs, other needs for schools or hospitals, and so that funding has just been dispersed. So the challenge is for how do engineers moving forward come up with better ways to design infrastructure systems, and then also how do you identify damage and maintain it, or repair the damage and maintain the facilities in a more sustainable manner. So that's what I'd hope to talk to you about a little bit. Just to give you an update or give you some information, the American Society of Civil Engineers does have a report card for each state. So you can also look at the California's report card. They don't have bridges explicitly here. It's tied into the transportation system. So let's start off with bridges. Bridge is classified as anything that's over 20 feet long. So some of these are really pretty short structures, but there are more than 600,000 highway bridges in the United States. And this plot shows you basically the number of bridges as a function of the age. So what you see is that about half these bridges are 40 years old or older. Now, I want you to think about the other types of engineered systems that you use all the time. Your automobile, I guarantee it's going to be younger than 40 years. Your cell phone, your computer, they weren't even available 40 years ago. So there is a fundamental disconnect between the types of structures that are part of this urban infrastructure, or the type of engineering systems that are part of the urban infrastructure, and what we accept are other systems that are available today. The design principles are very different. And as I mentioned, the society has grown. So 100 years ago, I don't think anyone would have guessed what Southern California would look like today. And so that factors into why some of this aging has occurred, or some of the deterioration has occurred. So as I mentioned, there are some really old bridges that are icons we have great national pride in some of these. The Brooklyn Bridge, for example, on the East Coast, and the Golden Gate Bridge here in California. I think all Americans recognize these structures, and maybe I'm going a bit overboard to say there's a sense of pride, but if something were to happen, I think it would be recognized as a loss. So if you look at a map across the entire U.S., these are bridges that, they're not unsafe, but they're having deterioration. And if there's enough deterioration that has occurred, they get classified as being structurally deficient. And so you see that there's a lot of these bridges concentrated in the East Coast, and that's because that's where some of our older cities are, but there are also a decent number here in California. So in order to ensure the safety of these structures, you've probably seen the load limit signs. So they limit the size of the vehicles that can cross these bridges. So I don't want you to feel as if there are a whole bunch of unsafe bridges out there. That certainly is not the case. The bridges are inspected fairly regularly. I'll give you a slide about that in a few minutes. But there is deterioration. I mean, if you look at this bridge in the photograph, you can see the rust, right? So rust we've lost some of the cross-section of the steel sections. You also notice this is a very narrow bridge. You probably don't want to be driving across this when there's a tractor trailer coming right at you. That's, as I mentioned, that's because some of these design standards have changed. Trucks have gotten considerably larger and heavier in the past 40 to 60 years. So I think the last picture really illustrates why infrastructure is problematic. So the first thing is we design these systems to last for somewhere between 50 and 100 years. But I think if you start thinking about what's Southern California going to look like 100 years from now, you realize how difficult that's going to be. I don't think anyone in this time frame would anticipate how much the population has grown, how heavy our trucks have become on the highways. The next is that every single structure is unique. So instead of saying, if I think of another big structure like an airplane, well, we have a couple models, and they're produced in a factory, but they're all by the same design. That's not what happens with these infrastructure systems. Everyone has unique conditions, and they're all done one of a kind in place. So that's very different also. And I think another thing that's incredibly important is that we're using public funds for the construction. That means all of us are contributing to the construction of these facilities. We don't want the gold-plated bridge, right? We want to make sure that we're getting our money's worth, so we have to focus on the initial cost. Unfortunately, what that sometimes tends to do, especially since we don't know what's going to happen in the future, is that the cost of maintenance can be high, and our budgets are tight. So we don't always have the money we need for maintenance and as much repair as we would like. And then the last thing is, it's not always easy to identify what the damage is. There are key structural elements that may not be visible after the construction is completed. And also, a lot of times the first indication that there's damage is very fine cracks. So these cracks may start off as something that's a little wider than a human hair. And yet think about the Brooklyn Bridge or the Golden Gate Bridge. They're miles, or Golden Gate at least is miles long. So it's very hard to find something as small as a crack that's initiating in a structure that's that large. So that early detection of damage is quite difficult. Even if you identify the damage, it can often take many, many years before a structure can be replaced. So this is the Tappan Zee Bridge. It crosses the Hudson River just north of New York City. Okay, this bridge was opened in 1955. More than 140,000 vehicles cross it every day. And what happens here is there's so much traffic going across the river that they actually have to change the lanes so that there are 5 lanes going with the direction of the commuters and 2 lanes going in the opposite direction. So in the middle of the day, they switch that. So this bridge is at the end of its functional life. It cannot accommodate the traffic need, but it also is at the end of its structural life. Yet when you go through the environmental impact studies, you go through all the structural design, it takes years to be able to replace the bridge, not to mention getting the funding to do it. So none of these things happen really quickly. Now, I mentioned a little earlier that one of the things that differentiates bridges from some of the other infrastructure systems is that they are inspected on a regular basis. This is because we had 3 major bridge failures between the 1960s to 1980s that really changed the way that bridge inspection was done, or the way bridges were treated. The first was the bridge in Point Pleasant, West Virginia. And this bridge collapsed, and what happened after that was they implemented a policy that all bridges had to be inspected at least every 2 years. So no matter how large the highway bridge is, anywhere in the country, you know someone is out there at least looking at it. Now, in 1983, there was a bridge that was classified as fracture critical that failed. Fracture critical means that if one piece fails or one component fails, that can cause a cascading effect and the entire bridge can fail. So we have much stricter quality control efforts in place for the fracture critical bridges. And I'll give you an example of that a little later on. The last one is related to scour. So if you remember, it was earlier this summer when the I-10 bridge connecting Nevada to California one of the supports was washed out. It was kind of like scour. Scour tends to be when you have a lot of water going through under a bridge. It undermines the foundation and the bridge collapses. So for areas where prone to flooding, they actually do underwater inspections to make sure that the foundations are still appropriate. Okay, so I've talked about why infrastructure is difficult. Let's talk about technology. There's all kinds of technology available today. I mean, the smartwatch that half of us are wearing or our smartphones have more sensors than probably they used when they sent the man to the moon, right? And so why can't we use some of this technology to take full advantage of monitoring infrastructure systems and identifying when the problems occur? So that's kind of the challenge I'd like to place out here to you. Why can't we do it? So to talk about this, well, we can do it, right? But there are some limits. There are a lot of buts. As I think I mentioned before, that the damage isn't uniformly distributed on the bridge. It tends to be concentrated in locations, and we don't always know where those locations are. So that makes it hard because when you're wearing a smartwatch, you can get your heart rate. There are some attachments you can do and get other information like your blood pressure, but they know exactly where to place those sensors because it's based on the human anatomy. Because each bridge is unique, those critical locations are not known in advance. If you put the sensor in the wrong place, it really doesn't do you any good at all. And I mentioned before, these critical structural elements may not always be visible, so that complicates things. You might not be able to see the damage as it's occurring. And as I mentioned, this initiation of damage is often hard to find. You have to look very closely, and when your bridge is a couple miles long, it actually becomes quite difficult to do those inspections. If you do put a monitoring system on, those costs tend to be fairly high. I'll give you an example of a bridge in Texas where the initial cost to install the monitoring system was over $1 million. It costs over $100,000 a year to maintain that monitoring system. So you obviously cannot do that for all the bridges, for the 600,000 bridges that we have in the United States. And then I think maybe most importantly, because each bridge is unique, and because you might need different types of sensors for each bridge, it can often be very difficult to extract just the right information from the measured data. So you might get totally overwhelmed with data and be unable to tell what the important information is. So let me give you a couple examples. Let's assume we want to put a monitoring system up. Well, we might be out in the middle of nowhere. There is not any type of power. And just placing the sensors, if there's no power, you've got to rely on batteries. Changing batteries, it could be a major ordeal. This happens to be a truck that's articulated that allows, so you're driving across the bridge, it allows you to inspect underneath. But you can imagine this is a very slow process, and you wouldn't want to be going out and maintaining your monitoring system on a regular basis. This is a bridge that I'll talk about a little later. It's in Texas, just south of San Antonio. It's a fairly major highway bridge. Well, it used to be. It's been replaced now. But when you go out to do the inspection, you're blocking several lanes of traffic. And so you've got 5 miles of traffic blocked up because you're doing that inspection. So I'm going to give you examples about 2 monitoring systems that I had the opportunity to work on since I've been at the University of Texas. In both cases, we had visual indications beforehand that the damage had occurred. That allowed us to know where to place the sensors and to decide what type of sensors to use. The information that we collected allowed the owners, TxDOT and their consultants, to develop an appropriate repair strategy for those bridges. So I think in these cases, they're both really success stories. So the examples I'm going to talk about are, it's a bridge on I-35. I-35 runs from Texas all the way up to Minnesota. And the example is a bridge that's just south of San Antonio. And then the second is the Fred Hartman Bridge, which is over the Houston Ship Channel. It's one of the major hurricane evacuation routes for the city of Houston. So this is a photograph, or this is a photo of the Medina River Bridge. This bridge was designed in 1935. Okay, so it's a very, very old structure. There were about 4,000 trucks that were crossing this bridge every day. So I guarantee in 1935, they were not envisioning these large tractor trailers crossing the bridge. But this was, up until about 2 years ago, this was still part of our interstate system here in the US. Now I apologize, this is my structural engineer coming out. The span here is just under 300 feet, and it had 2 internal supports. What's interesting, though, is it's what's called a statically determinate bridge. So there's no inherent redundancy, and if there's failure at one location, it could cause the entire bridge to come down, to fail. The other thing that's interesting is this is a riveted bridge. So in 1935, they didn't have the ability to roll steel sections. So this was, the longitudinal girders have 4 different angles, 2 at the top and 2 at the bottom, and then a very thin plate, and all those are riveted together to form the main structural elements. In addition, there are some cover plates. In the areas where the highest stresses were anticipated, they put some cover plates at both the top and the bottom of the cross-section just to improve its ability to carry these stresses. Now, when the bridge was originally designed, it had 2 lanes of traffic, and it was 12 feet wide for each lane. This carried traffic in both directions across the bridge. Those are incredibly narrow lanes, especially if you're thinking about an interstate, right? So in 1974, they widened the bridge, and they also turned it into just northbound traffic. So the traffic lanes are at least a little bit wider now. They were 14 feet in each direction. It still wasn't very wide, and there still isn't a shoulder in case you have trouble. But what they did when they installed those overhangs was they put welds on the bridge. And welds were something that weren't available in the 1930s when the bridge was built. Well, these welds, because there are only 2 girders that form the cross-section of this bridge, This bridge is in the category of fracture critical, meaning that if you have a critical element fails, it's likely the entire bridge will come down. So a very detailed inspection is required. It's called a hands-on inspection. You can see here underneath the bridge, about 300 feet long, the TxDOT employees actually go through. These are the tools that they use for this inspection. They've got a screwdriver, a wire brush, and a hammer. And they go and they tap and they scrape off dirt and they just look. And so you've got some kind of bucket trucks, so they're up, hands-on. They are immediately adjacent to that bridge, and they are looking at every single component. So it takes quite a bit of time for this inspection to occur. What I want to show you is the type of damage that they found. And in order to see that damage, you've got to be about 2 feet away. So to try to give you a little perspective, we're looking here, we're underneath the bridge, and we're looking at the longitudinal girder is right here. So this is the direction that the traffic would flow on the bridge. There are a whole series of floor beams, which are much shallower, that are tie in right below the slab. So I'm going to be showing you that connection. Now I'm up about even to the bottom of the bridge. Again, I'm going to zoom in on this connection, and I'm going to go up to the top. And here's the inspector's hard hat, so the inspector is getting right up in there. And then this is what it looks like. You're thinking, okay, this is a little hard to see. I agree with that. That happens to be a crack. So a crack is growing. But, the flange there is only about 4 inches wide. So this is why I was telling you it's really hard to find damage, because I've got a 300-foot-long bridge. I've got a crack that is less than 1/20th of an inch, and it's about 3 inches. Yet this is a real cause of concern. The other cause of concern was we put some gauges on this bridge to try to figure out what the stresses were. And this happens to be a stress history. So as a truck crossed over the location where our instrumentation was, it generated a big pulse. This pulse was 20,000 pounds per square inch. Now, I know that unit doesn't mean a lot to you, but it's a very large stress. The damage that's induced by these repetitive loads is called fatigue damage, and it's proportional to the cube of the stress range. So if I have a stress range of 1 KSI compared with 10 KSI, the 10 KSI stress range will be 1,000 times, induce 1,000 times, be 1,000 times more damaging, because the fatigue stresses, or the fatigue damage goes up by the cube. So this was a tremendously large stress range. Now, we didn't record many of them, but just the fact that we got one this large was really disconcerting to us. The other thing that we did is we went out and we knew where some of these cracks were located, so we put what's called a crack propagation gauge right at the tip of the crack. It's a whole bunch of little wires, and what happens is as the wires break, the resistance of this gauge changes. So you get a feel for how fast that crack is growing. And we were having trouble with our solar panels, so we don't have continuous data here. But what you see is this blue line started off here with a resistance indicating that the gauge was intact. And within about 6 or 8 weeks, it had jumped, indicating that the crack had grown about 0.4 of an inch. Now, we only put 2 up. You can see the other one is pretty stable. So we had a situation where we had very, very large stresses that we measured. We also knew that these cracks were growing quickly. We went to the Texas Department of Transportation, told them about what was happening, and they had actually been concerned about the bridge. They didn't have the quantitative data that we had from monitoring, but they had been tracking these cracks because they had been going out every year to see how fast things were going. What they decided to do was essentially cut out a section of slab every place where the floor beams intersected the girders, and they reinforced those with a series of plates. So here you can see the workers have dug out the holes. Now, these circular holes here, unfortunately, we didn't get to take the picture before they drilled the holes. That's for the repair scheme. But what I want to show you is this yellow line is one of those cracks that was growing so quickly. And you can see here it's propagated across the entire flange of that channel. Here's another one, another location. Okay, the crack has a different form to it, but it's exactly the same. And what you saw in both of these cases was this was the weld that they added to the bridge in 1974 when they wanted to expand the width. That was what is causing the problem. As it turned out, there was another bridge that was exactly like this in another part of the state that had never been widened. It's still in use. It doesn't have any cracks at all. But because this was on an interstate, had so much traffic, and those lanes were just too narrow, they went in and they put those welds in, and that's what caused the problem. So for this repair, they just did a really quick and dirty strategy. They put a series of plates on top so that there was an additional pathway so that the stresses could be transferred through these plates, which they had bolted on. And this is looking from underneath just so you get a feel for it. Now, we were lucky. We had been out monitoring this bridge for over a year, and we happened to catch that entire construction sequence. So this blue line shows you how large the stresses were before they did the repair, and the orange line showed what happened after the repair. And you can see that it shifted considerably to a smaller stress range. So in this case, that repair strategy was extremely effective. Now, let's go back and review a few things here. That we knew where to put our sensors because we knew there were cracks. So that greatly simplified the fact that we were looking for that needle in the haystack. Secondly, they developed a repair strategy that just provided an alternate load pathway for the top flange. Our monitoring system demonstrated that strategy worked very well. What this allowed them to do is instead of having to replace that bridge immediately because those cracks were growing, they realized they had about an 18-month to 2-year window to do it because they had invested in their repair strategy. So as of today, this bridge has been removed from the inventory. There is a new bridge there. But because it was safe while they kept it in service on the interstate. Now, another option would have been to put load sign or to post it and limit the traffic load. But that would have been incredibly disruptive because, as I mentioned, this is one of the major corridors between Mexico and Texas. And so there are just a huge variety of trucks that are crossing it. So I think this was an example where our instrumentation really helped us to quantify the extent of the damage and gave them confidence that the repair strategy had worked well. That was a bridge that was at the end of its life. I want to talk now about the Fred Hartman Bridge outside of Houston, which was at the very beginning of its life. So the bridge opened in 1995. It is basically 2 parallel bridges, and it's called a cable stay bridge. And so each of these stables is anchored at the top, and it's also anchored at the deck. So unlike a suspension bridge, they're not continuous. They're just individual segments. Now, the following video was recorded in April of 1996. So this is a brand new bridge, right? This is one of the major hurricane evacuation routes from the 4th largest city in the U.S. And it's not even a year old. This is not a good sign. I mentioned there are 192 stay cables on this. It was over 180 where there were weld fractures of some sort. Now, luckily, this weld right here is really not part of the structural system. So those were easy to repair. The stay cables themselves were the primary load-carrying mechanisms. And the stay cables were steel strands, pre-stressing strands. And so they're arranged in a pattern. These cables were between 200 and 650 feet in length. And we've got somewhere between 19 and 60 strands in the entire cable. Oh, thank you. In the entire stay cable. So the trouble is you couldn't just open up the stay cable and look to see was there any damage. And that's because in order to provide corrosion protection, they have a polyethylene duct around the steel members, and then they fill it with a cementitious grout. So the only way that you can see what's happening is basically to dig into it and destroy the strand. So obviously that's something you don't want to do if your bridge is brand new. So I was actually lucky to be part of the team that went in to try to evaluate what was happening with the bridge. And because each of these cables were anchored at the 2 points, we could do some very simple tests to try to figure out what was happening in the bridges. So all of you have seen the violin, right? You've seen the concertmaster get up and play the A string. That gives a 440 frequency, and that's how the entire orchestra tunes. Well, you can think of these stay cables as essentially being a really big violin string. And the violin string, this is the frequency. We'd talk about the first mode of vibration. So it depends on the length. Well, the length of the violin string is fixed. The mass is fixed because you've got a different mass for each of the 4 strings. And when they turn the knobs, they're changing the tension. So that's what they do to tune it. Okay? Now, for a cable, and I apologize for the differential equation. I'm not going to go into it. It's a little more complicated, but it's still the same basic idea. It's still a really long string. So we went out and we started pulling on these strings. And what we tried to do is compare what did we measure with what did we expect it to be based on the design tension. And these are all the dots. The 192 dots are shown here. What you see is they're all over the place. Some are high by 30%, the forces, the difference between what you would calculate the force to be and what you would get from the vibration. Some are low by 30%. They're just all over the place. And kind of the decision that was made was, we're going to expect some scatter here. Let's repair it. Let's make sure that we don't have those big vibrations. And then we'll do something to try to make sure that we can monitor these strands to see if more damage occurs. So this was one of the first cable stay bridges that was built in the U.S. And around the same time, they were noticing the same type of cable vibration in many of these bridges around the world. And it turned out that the damping is actually quite low. And so when the wind starts blowing and you get a little bit of light rain, these bridges tend to vibrate, and that's what we saw in the video. So what they decided to do was add a damper, an external damper, at the bottom of every single cable. As the cable then started to move, this helped to damp out those vibrations. The other thing they did is higher up in the cables, they tied the cables together. And so because each cable is a different length, it has different vibrational properties, by tying them together, you get a stiffer system. So they have not seen any more of those large amplitude vibrations on the bridge. So the repair strategy worked. Now, the problem, though, is they didn't know how much damage had occurred to the key elements, those pre-stressing strands, before they did the repair strategy. And there really is no way to determine how much damage had occurred because we couldn't do the visual inspection. So a company came forward with a proprietary system where they would basically put 3 different instruments on every single stay cable, and they would listen for the pop that's made when you get a wire break. And the Texas Department of Transportation thought, okay, that sounds good, but we want to verify that in the laboratory beforehand. And so that's where the main part of this project that I worked on. We had a much shorter version of the stay cable, but we built it the same way. Our cables were about 32 feet long. And we used the same cross-sectional properties. And we had a big actuator that was in the middle that just moved the cable up and down. and we generated fatigue damage. And so this allowed us to understand how does damage accumulate in these big systems, and where is it located? What are the key issues? We also had this proprietary system on all of our stays, or all of our test specimens, so we could have a better understanding. We could really go in and check afterwards, did these systems work? Okay, so the first thing we noticed was that as you start getting damage, it tends to be a couple things are, only a couple happen at first, and then it's like popcorn. I think the popcorn analogy in the microwave is a great example. You put the bag in, nothing happens, you get pop, pop, and then everything starts popping. That's very similar to how the damage in these wires occurs. What happens here is that the wires start rubbing against each other as the cables are vibrating, and you get a product that's much harder than the steel. And so it causes a friction, it heats up, and then you get a break in the wire. And so at first it's a very gradual process, but then it accelerates. Okay? So we couldn't give the Department of Transportation an exact number of wire breaks that they could accommodate. But what we could tell them at least was, if you monitor this all the time, if you start hearing a bunch of pops, you're in trouble. But if you don't hear any, then you're probably in good shape. And so that's what we did. So we had the advantage that after the test, we could tear our specimens apart and we could look at the damage. So we're looking here at a 0.6 of an inch diameter pre-stressing strand. There are 7 individual wires here, and you can see right here, we can see at least 3, I think there's 4 right here. 4 wires have broken in this strand. If you look at the end of it, okay, you can see the individual wires. And if we zoom in a little more, what we can see is we had a location where the crack propagated. The crack grew very slowly, and then the tension in that wire exceeded the capacity, and it fractured. And that's the pop, and that's what the acoustic monitoring system would pick up. And so in this case, you can see 3 of these points. Okay, we also found that they tended to be located at the ends, but that didn't really matter. It doesn't matter where it's broken along the entire stay. If they're broken, you're in trouble. So this is what the data would look like. This type of sensor is very much like what they use for earthquake monitoring. It listens all the time. It has a memory, and then if it hears a pop, it records from a little before that pop occurred. Same thing they do for the earthquake monitoring. And so by having 3 or 4 different sensors on each strand, you can identify the location. So for the Fred Hartman Bridge, I think this really was a success story, whereas we started off with a bridge that was brand new, it was a critical structure, and it was having serious problems. TxDOT did a repair strategy that worked. The acoustic monitoring system, we demonstrated in the laboratory that it was doing a really good job of catching the damage. And although we can't tell them exactly how much damage occurred during those initial incidents that I showed you in the video, because they're monitoring continuously, they know when wire breaks occur moving forward. And so they've had a few. They've been distributed among different stay cables, so they're not really worried about it. I think I told you, this monitoring system, though, it cost over $1 million to install, and they pay an annual fee for this type of monitoring. So the importance of the structure and the high risk of damage is why they're willing to provide that much money for this type of this monitoring. This is another bridge that's located in Louisiana. It also had some cable problems. I think it was more related to corrosion. Less than 20 years after the bridge was built, they actually replaced every single cable on that bridge. So that's your other choice, is you can go in and just replace all of them, but that's extremely it costs a lot of money, and it takes a lot of time in construction. And for the Fred Hartman Bridge, it would have been very difficult to do it because when they had built the bridge, they used a really large jack at the top of the structure. But when they closed off the piers, that same jack could not get in. So they'd have to stress each individual strand one at a time. And I mentioned some of these cables have like 60 strands in them. So it would have been a very, very time-consuming and difficult construction project. So I started off by telling you that we've got a problem with infrastructure in the U.S. And what can we do, right? I'm hopeful that our new designs are going to be better than some of our older designs. But we have a large component of old infrastructure in the U.S., and we have to find ways to maintain and repair that. So there are a lot of very exciting new technologies that are being developed that can be used for infrastructure monitoring. I'm not optimistic that it will be widespread adoption, though, because these costs are going to be high. And also, it often is not easy to get the information you want from the monitoring systems. In order for it to work effectively, the information that you collect has to directly influence the decision makers. I know that when we've talked with TxDOT about doing research projects where we develop monitoring systems or sensors for them, they think it might be great, it might work in the laboratory, but you put it out in a difficult environment, an extreme environment, and it's very difficult for them to maintain those monitoring systems. So that's why they prefer to have a company that they pay to monitor rather than invest in trying to do that by themselves. I think the other thing is that the costs of this are going to be quite high. So that will be what limits the widespread adoption of monitoring systems. And the funding is a critical issue because as I started off saying is that there is really there are so many things that we as taxpayers need to invest in this country. And infrastructure is not always the highest priority, mainly because the timescales are so long. Okay, you know when you have overcrowding in a school and you need to replace that school or that hospital. But the life of infrastructure, it's 10 years, it's another 20 years. Well, our political process is such that elected official will probably not be in office in that time. So very often, the infrastructure has the least priority. And I think, there are a lot of cases where a specific problem is identified. They'll call in a consulting engineer, go out and install monitoring, really help identify the problem, and that focuses into the repair strategy. So I think that's being used quite often now, and that's probably the much more common way you're going to see infrastructure monitoring. Now, I'd like to close. As I mentioned, this long-term monitoring, it's very few cases in the U.S. where it's really been used, and they have to be a critical structure. I want to end with a bumper sticker that I saw a couple years ago in Austin. We were talking about having a light rail system in town because our traffic was so high. And I think it really highlights why infrastructure is important, but maybe not always a priority, is because it's a society gets to decide where to make the investments. And a lot of times things like schools and social services are going to rise to the top more frequently than infrastructure. So ASCE will tell you, write to your congressman, let them know you think infrastructure is important. I agree with that, but I still think that this attitude is going to prevail. So in closing, I do want to thank the many colleagues that I've worked with on these projects. The Texas Department of Transportation and the National Institutes of Standard and Technology funded the projects that I discussed. I had the great pleasure of working with three senior colleagues. Carl Frank and Todd Helwig were my colleagues at UT Austin. Randy Poston is a practicing engineer in Austin, and then a whole variety of graduate students. So I want to thank you very much for your time, and I would be happy to answer any questions you might have.